Have you ever looked at a massive skyscraper and just thought, how in the world is that thing not falling over? Or maybe you've driven across a bridge and had that split-second thought about the insane amount of weight it's holding up. Well, I can tell you it's not magic. It's an incredible field of engineering called statics. And today, we're going to peel back the curtain and see the world like an engineer does, not as a world of concrete and steel, but as a world of invisible forces all locked in a constant, delicate dance of perfect balance.
I love this quote from a seasoned engineer because it just gets right to the heart of it. Statics isn't really about crunching numbers. It's a completely different way of seeing the world around you. It's about training your mind to visualize this invisible web of forces that keeps absolutely everything, from the chair you're sitting on to the tallest buildings on Earth, standing strong.
So how do we even begin to understand this invisible world? Well, the very first, and I mean the most important step, is to make those forces visible. Before an engineer can do a single calculation, they have to be able to map out every single push and pull acting on a structure. It's the absolute foundation that everything else is built on.
Right, so when you or I see a building, we see glass and steel. But an engineer, they see a battlefield, a completely balanced but dynamic battlefield of forces. You've got gravity constantly pulling down, the ground pushing right back up, and every single beam is either being stretched apart or squeezed together. To make any sense of it all, they need a map of this invisible war. And for that, they have one incredibly powerful, yet surprisingly simple tool.
This right here is the free body diagram, the FBD. And let me tell you, it is the key to everything in statics. What you do is you basically take an object, you isolate it in your mind from everything around it, and you draw every single force that's acting on it. Its own weight, the support from the ground, any random pushes or pulls, it all gets an arrow on the diagram. Seriously, getting the FED right isn't just the first step. In a lot of ways, it is the solution.
Okay, so once we've made all the forces visible on our diagram, we need a toolkit to actually work with them. And that's because these forces, they rarely push in simple, straight lines. Nope, they come at you from all sorts of weird angles.
So on this slide, you're seeing the two main ways forces are described. The first one, using an angle, yeah, that's pretty standard. But that second method, the slope triangle, that's what the pros use. It's just faster. You're working with simple ratios, not fumbling with trig functions and long decimals on a calculator. Trust me, on a big project with hundreds of forces, that speed and the way it cuts down on errors is a huge, huge advantage. So the game plan is this simple three-step process. And it doesn't matter how many forces are pulling on an object, the method is always the same. First, you break every single force down into its simple up-down and left-right pieces. Then, you add up all the left-right pieces and all the up-down pieces. And finally, you combine those two totals to find one single resultant force that does the job of all the others combined.
But hold on, forces don't just push and pull in straight lines. They also make things want to spin. And this rotational effect is the second critical concept in our engineering toolkit. It's called a moment. Just think about trying to loosen a really stubborn bolt with a wrench. You're applying a force, right? But what really matters is the turning effect of that force. That's a moment. And you know from experience, the longer the wrench, the easier it is to turn that bolt. That's because you're increasing the distance, which gives you way more leverage and a much bigger moment. Okay, here's another brilliant engineering shortcut. So let's slow down for this one because it's a game changer. Trying to calculate the moment of a force that's coming in at a weird angle can be a total pain because you have to find that exact perpendicular distance. But Varignon's theorem is our easy way out. Instead of dealing with that one tricky angled force, we just break it down into its simple up, down, and left-right components. Then we calculate the moment for each of those super easy components and just add them together. It's a way simpler calculation, and it saves a ton of time and headaches. All right, now we've got our toolkits. We understand forces, and we understand moments. Now we can actually start to analyze real-world structures and see how they're designed to achieve that perfect, beautiful balance.
In statics, we're mostly looking at two main types of structures. First, you have trusses, like the Eiffel Tower. They're these beautiful networks where every single piece is either being purely stretched, that's tension, or purely squeezed, that's compression. Once you know what to look for, you'll see them everywhere, in electrical towers, crane booms, even the roof of your house. Then you have frames. Frames are basically the skeletons of almost every office building you've ever been in, where the parts have to handle not just pushing and pulling, but also bending. Now, when we want to figure out the forces inside a truss, there are two main ways to go.
The method of joints is the straightforward way. You just go through and analyze every single connection one by one. It works. But the method of sections, that's where things get really clever. Say you only care about the force in one specific beam in the middle of a massive bridge. You don't need to analyze the whole thing. The method of sections lets you zoom right in on that one piece and get your answer in just a couple of steps. It's an incredible time saver.
So here's how the magic trick works. You make an imaginary cut right through the truss, slicing through the piece you care about. Then, you use our old friend, the moment. By cleverly picking a pivot point where two of the unknown forces meet, their rotational effect on that point becomes zero. They have no leverage, so they literally vanish from the equation, leaving you with one simple calculation that solves for the third and most important force. It's just an elegant and incredibly powerful way to solve a complex problem.
Okay, so we've covered the theory, but a massive part of engineering is the practical wisdom, the stuff you learn from experience. These are the unwritten rules that separate the beginners from the experts. Ready for some pro tips? This is the good stuff. First, symmetry is your absolute best friend. If a structure and its loads look the same on both sides, guess what? Your calculations are literally cut in half. Done. Second, learn to spot zero force members. These are parts of a structure that aren't actually carrying any load for a given setup, so you can just ignore them and make your diagram way simpler. And finally, the golden rule of all golden rules. Always, always check your units. Mixing up meters and millimeters is the #1 trap, and it can lead to catastrophic failures. So, as we start to wrap this up, it's pretty clear that statics is so much more than a class you take. It's a way of thinking. It's a disciplined approach to seeing and understanding the physical world. So what are the biggest takeaways here? Let's call them the 3 golden rules of statics. Rule number 1, draw first, calculate later. That free body diagram isn't just a sketch to get you started. It's the roadmap to your entire solution. Get it right, and the math almost solves itself. Rule number 2, always do a logic check. Ask yourself, does this answer actually make sense in the real world? Developing that gut feeling, that engineering sense, is just as important as the math. And finally, rule number 3, never forget that this is the foundation of everything we build. Every skyscraper, every bridge, every car, they all stand on these fundamental principles of balance. So the next time you're just out and about, I want you to take a second. Look at a building or a bridge or even just a street sign. Try to see it with these new engineering eyes. Can you start to visualize those invisible forces pushing and pulling, all held in that perfect, silent balance? What hidden forces can you see now?